Hello everyone. Now that you have completed your lecture on hematopoiesis in general, now we are going to switch our focus over to the process of erythropoiesis. And what you are going to learn in this session essentially will be on erythropoiesis itself and how it is regulated. We are going to also describe some of the common causes of anemia. So when erythropoiesis and its regulation is disrupted, what kind of disorder can it cause? In particular, anemia. We will also be looking at some of the common clinical tests to assess or evaluate anemia itself. What we are also going to do is to try and apply the clinical tests that you have learned and see how we can assess anemia using these tests. But this is something that we will do, not during this recorded session, but in the discussion later on when you see me live. Right? So please attend the live session as well. Alright, let's get started. Now when it comes to erythropoiesis, what we are talking about is a process that takes about 14 to 21 days. It's a process that takes place inside the bone marrow itself. And it all started with, as what you have learned from the hematopoiesis lecture, the myeloid stem cells. Now when it comes to the myeloid stem cell, the first trigger that stimulates the process of erythropoiesis will be its differentiation and proliferation into pro-erythroblasts. And this process requires your erythropoietin. Right? Upon stimulation by your erythropoietin, it's a growth factor. That's when your myeloid stem cell starts to proliferate and differentiate into your pro-erythroblast. After pro-erythroblast is formed, that's when it starts to divide further into many erythroblasts. Now this further division of your pro-erythroblasts requires DNA synthesis, and that's when folate and vitamin B12 is required. In other words, for those who are practicing a poor diet, for example, and there's deficiency in folate and vitamin B12, DNA synthesis will be affected and the process of erythropoiesis will be affected as well. And this is something that we will be discussing later on when we talk about the different causes of anemia. Following the formation of erythroblasts, that's when there will be multiple stages of maturation until a premature erythrocytes is being formed. That's what we call reticulocytes. Right, so you can see here that the arrow is actually summarized into dotted arrows because this involves a lot of stages, which I have kind of simplified in one broken arrow. But essentially what you need to know in these multi-stages of maturation is that the erythroblasts will start to be filled with hemoglobin. And of course, the synthesis of hemoglobin will require iron. And hence, with iron deficiency, the process of erythropoiesis will be disrupted. And that's how iron deficient anemia comes about. Right? So when erythroblasts are being filled up with hemoglobin, that's when the red blood cell starts to grow in size as well. So what happens is that if there's insufficient hemoglobin being synthesized, the red blood cells being formed would not be able to achieve the necessary size because it's simply not squeezed with enough hemoglobin in them. Okay, during these multiple stages of maturation, other than the filling up with hemoglobin, what happens is that the nucleus in the erythroblast will also be reabsorbed or being extruded, right? So why so? Because this actually creates more space for the red blood cells to be filled up with more hemoglobin. And what would result from this process would be just reticulocytes that has remnants of organelles, for example, endoplasmic reticulum, which also explains why your premature RBC is also called reticulocytes, because when you look under the microscope, you actually see remnants of the reticulum, right? So these black lines here are actually the remnants of your endoplasmic reticulum, which gives rise to your reticulocytes. So reticulocytes is important. Why so? Now, once reticulocyte is formed, it actually migrates into the capillaries through a process called diapedesis. So it has a very flexible membrane that allows it to squeeze through the spores, the tiny pores of your capillaries. And once it enters the circulation, that's when it starts maturing into your mature red blood cells. Now, I mentioned that reticulocytes is important because the maturation of reticulocytes to RBC takes only 1 to 2 days. So you don't tend to see a lot of reticulocytes in the circulation. At any point of time, there's usually about only 1% of reticulocytes in the circulation. And this reticulocyte count here actually provides an indication on the activity of the bone marrow itself. In other words, it's an indicator of erythropoiesis. If you see too little reticulocytes in the system, you know that erythropoiesis is not functioning well. On the contrary, sometimes reticulocytes counts might be way more than 1%, and that is also an indication that something is causing very high activity of erythropoiesis, and we have to find out why. Okay, so once mature RBC is being formed, the RBC would reach a size of about 7 to 8 micrometer in diameter. It has flexible membrane, so what this means is that it would then be able to squeeze through the tiny pores, especially through the reticular endothelial system. Reticular endothelial system is something like your spleen that has very convoluted and tiny capillaries. And why this reticular endothelial system is important is because when your red blood cell age, say about 120 days, it starts to lose the membrane elasticity, and it would not be able to squeeze through the tiny pores from your spleen and your reticular endothelial system. That is when it starts to burst, or that is when it starts to get trapped in your spleen, and your macrophages in the spleen will start to engulf it and remove the aged red blood cells from there. Alright, as you will learn from Dr. Kenneth Barnes' lecture after this as well, the RBCs that are being engulfed and degraded by the macrophages, the hemoglobin will actually be metabolized as well, and as a result, bilirubin will be actually released into the circulation, and this metabolism of and clearance of bilirubin is something that you will learn later on in Prof. Kenneth Barnes' lecture as well. Alright? Okay, so this sums up the entire process of erythropoiesis. Now, what we are going to discuss next is actually how exactly is erythropoiesis being regulated. And this is important because if you learn from Dr. Natasha's lecture on homeostasis, what all physiological process always strive to maintain a physiological balance, and likewise for erythropoiesis, there's always a need to make sure that the amount of red blood cells in the bloodstream is always maintained at a sweet spot, at an equilibrium that meets the oxygen need of the body. So in order for this to happen, erythropoiesis needs to be regulated in a tight system, and how this is regulated is what we are going to discuss next. So you have learned that erythropoiesis takes place in the bone marrow, and for erythropoiesis to be kick-started, it needs the synthesis of EPO, or erythropoietin, right? And one of the main factors that stimulate the production of EPO is actually fluctuations in the partial oxygen pressure in the circulation. So arterial partial oxygen pressure can actually be affected by multiple factors, and all these factors will affect the eventual synthesis of erythropoietin as well as the erythropoiesis process. For example, in patients with anemia, right, when there's insufficient oxygen delivery capacity, that will affect oxygen partial pressure in the blood as well. Those with cardiopulmonary conditions, for example, will have oxygen supply being affected, which will also affect PaO2 too. In conditions where you go up to high altitude, when atmospheric partial oxygen pressure is low, that can affect PaO2, or in those who always undergo endurance training, endurance exercises, there's increased oxygen consumption, that may actually reduce oxygen availability in the blood as well. All these are actually stimulus that may trigger increased erythropoiesis. How this happen? It's through the production of HIF-1 alpha, hypoxia-induced factor 1 alpha. So whenever there's low partial oxygen pressure, HIF-1 alpha, which is a transcription factor, would be synthesized and released into the circulation. Now this would then stimulate the production of EPO by the kidney, and as a result, there's increased EPO being released in the circulation. Now, of course, EPO, it's a growth factor that stimulates the process of erythropoiesis, and that is when increased red blood cells is being produced, and hence the return of oxygen or the increase in oxygen capacity in the circulation. Now, when there's increase in oxygen capacity, of course, this would create a negative feedback loop, because that would then reduce or relieve the initial stimulus for EPO production. Because when O2 level is returned, the stimulus for HIF-1 alpha is reduced, and EPO will be reduced as well. So this creates a negative feedback loop that allows erythropoiesis to be constantly regulated, and also to allow oxygen delivering capacity to be constantly maintained at a sweet spot. The problem is what happens if the regulation of erythropoiesis goes haywire. Right? And that's where I bring back the concept of homeostasis, which you have learned from Dr. Natasha's lecture previously. So if you recall from what you have learned, the process of homeostasis essentially is a physiological process that always seeks to return the body's processes back to its initial equilibrium. When there's any disruption in the equilibrium, there will be some physiological process that seeks to return it back to normal. So there's always a balance between clearance or reduction on a particular system with its production of gain in a particular process. And this is likewise applicable to your production of erythropoiesis as well, production of red blood cells as well. Alright, so when we look at erythropoiesis, there's always a need to balance the loss of RBC versus the gain or the production of RBC itself. When it comes to the factors that affects the loss in RBCs, we're talking about factors such as the usual clearance of red blood cells, or when there's acute blood loss, for example, somebody involved in an accident. There can also be instances where there's immune disruption of red blood cells, for example, when there's transfusion of wrong blood group, or when there's an autoimmune disease that hits our own RBC. That's when hemolysis or breaking down of the red blood cells happen. Of course, there can also be genetic defects that affects the function of the hemoglobin, and hence that may affect the loss of RBC as well. So these are many factors that can potentially increase the loss of red blood cells. Of course, all these factors needs to be counted by erythropoiesis or the gain in RBC. And there are also factors that affects the process of erythropoiesis. As what I've shared previously, hypoxia is one big stimulus for increased erythropoiesis. Of course, when erythropoiesis happens, the necessary nutrients needs to be there as well. For example, iron. For example, folate, as well as vitamin B12. There are also circumstances when erythropoiesis goes out of control. For instance, in neoplasia, where cancer formation actually results in uncontrolled proliferation of red blood cells. Or there are also instances when there's blood doping or artificial injection of EPO to enhance the production of red blood cells. So then all these factors needs to be balanced in order to achieve an equilibrium in the amount of red blood cells in the body. And when there's disruption of this balance, for example, in situations where there's more disruption of red blood cells than its production, that's when anemia happens. Or on the contrary, if there's more production of red blood cells as compared to the rate of loss, that's when polycythemia happens, too much red blood cells. This condition is quite rare. It happens when there's neoplasia, for example, or when there's artificial blood doping, where EPO is being artificially injected in the body. But for this particular recorded session, most of our focus will be on anemia itself. Now we know that this derangement or the disruption on the equilibrium in erythropoiesis will result in all sorts of hematopoietic disorders. The question here is that how can we assess the erythropoietic system and its dysregulation? And to answer this, we need to know what kind of tests are available for us to assess the blood system itself. And for the blood system, in terms of diagnostic tests, there are actually a whole range of diagnostic tests available today. Full blood count, for example, is a common one. We have also reticulocyte count and also the peripheral blood film. These top three here are the three diagnostic tests that we will be focusing on for this particular recorded session. But there are also other diagnostic tests that are also valuable, which we may not be spending a lot of time to discuss on it, but that is something that you will pick up along the way as you go through your clinical rotations or in some of the lectures later on. So for example, bone marrow aspirates will be something that we can do to evaluate the integrity of the bone marrow. We also have bilirubin and ferritin level tests. This is something that you can or you will learn from Dr. Ben's lecture later on when you learn about heme and hemoglobin metabolism. Okay, but as what I said, we'll be focusing on the top three here. Thank you.